Imagine you and a friend are starting out at different spots in a park, and you're both walking in perfectly straight lines. Sooner or later, your paths might actually cross. Well, math gives us this incredible way to find that exact meeting spot without anyone having to walk for miles. All right, let's get into it.
So, yeah, this is really the big question we're digging into. It doesn't matter if we're talking about two moving objects, two different business plans, or just two simple lines on a graph. What we want to know is how do we find that one single unique point that they both have in common?
All right, so this crossing point, this meeting place, what do we actually call it in the world of math? Let's give it its proper name.
What we're really talking about here is a system of equations. And don't let the name scare you. It's just a fancy way of saying we've got a set of two or more equations that we're looking at the same time. You can think of each equation as its own path, and our whole goal is to find the one point that satisfies all of them. I just love this way of putting it. It's so intuitive, right? The solution isn't just some random answer we pull out of thin air. No, it's the specific coordinate, the one spot that is part of both stories. It's the point that lives on both lines at the exact same time. So, how do we find this point? Well, the most intuitive way, the way that makes the most sense visually, is to literally draw a map of the paths. Graphing is just fantastic because you can literally see the answer right in front of you. You just plot each line on the graph and boom, the point where they cross, that's your solution. It's like a visual confirmation of that meeting spot we've been talking about. Okay, so let's try it with these two equations. For the first one, we'd start down at -3 on the y-axis, right? And then we use that slope of 2, which just means up 2 over 1, to draw our line. For the second one, we start way up at +5, and its slope -2/3 tells us to go down 2 and over 3. So you can already picture it. One line's climbing pretty steeply while the other is kind of gently falling. Where do you think they're going to meet? And there it is. If we plot them accurately, you can see they cross at exactly one point, the coordinate 3, 3. And what this means is that when x is 3, y is 3 for both lines. We can even do a super quick check. For that first equation, is 2 times 3 minus 3 equal to 3? Yep, it works. This visual method is awesome when the answer is this clean.
But here's the catch. What happens if the lines meet at, I don't know, x equals 3.147? Suddenly, graphing becomes a huge headache. It's really imprecise, it's super hard to read exact values if they're fractions or decimals, and it just gets clumsy if the intersection point is way off the page. So, we need some more precise tools in our toolbox.
Okay, so that brings us to our first algebraic tool, which I like to think of as a really clever, strategic shortcut. The substitution method is going to be your best friend when one of the equations has already done some of the heavy lifting for you. When it tells you flat out what y equals or what x equals. The logic here is actually pretty beautiful. First, you get one variable all by itself in one equation. Then, you take that expression, whatever it is, and you plug it in, you substitute it into the other equation. And just like that, you've created a brand new equation with only one variable, which is way easier to solve. Once you have that first answer, you just plug it back into one of the original equations to find the second. It's a really clean, step-by-step process. Now, for our second algebraic method, if substitution is the clever shortcut, think of this one as the power tool you bring out when things are a bit more complex. So, the elimination method really shines when your equations are all neatly lined up in what's called standard form, with the x's over the x's and the y's over the y's. The goal here is so simple, but so clever. First, you get both equations into that standard form. Then, you might have to multiply one or even both equations by a number so that the coefficient for either x or y becomes a perfect opposite, like a +5 and a -5. Why? Because when you add the two equations together, that variable just cancels out completely. It's eliminated. From there, you just solve for the variable that's left and then plug that answer back in to find the one you eliminated. So, here's the deal. The most crucial part is choosing the right tool for the job. You can think of this as your little cheat sheet. If you look at a problem and you see a variable that's already isolated, you see a y equals or an x equals, substitution is almost always your fastest path. But if you see both equations are already lined up in that nice standard form, elimination is probably going to be way more efficient. Trust me, choosing the right method from the get-go makes all the difference. But what if the two paths never cross? Or what if they're actually the exact same path? We've got to look at these special cases.
So take a look at this system. Notice anything a little, familiar? The slope in both equations is 2. But look at the y-intercepts. One's at +1 and the other's at -3. This means the lines are rising at the exact same rate, but they're starting from totally different places. Visually, these are parallel lines. They just run alongside each other forever and ever, and they will never, ever intersect.
So what do you think happens when you try to solve this with algebra? Well, you'll work through all the steps, and you'll end up with a totally nonsensical statement, something like 0 equals -4. Now, when the math spits out something that is clearly false, that's not you making a mistake. That's the system's way of screaming at you that there is no solution. The paths just never cross. Okay, now what about this system here? At first glance, they look pretty different, right? But if you take that entire second equation and divide everything by 3, what do you get? You get y equals x plus 2. Whoa! These aren't two different lines at all. They are the exact same line, with one of them just wearing a clever disguise. And when you try to solve this one, something else cool happens. The variables will all cancel out, and you'll be left with a statement that is always true, like 0 equals 0. This is the mathematical way of saying, well, of course this is true. These lines are the same. It means they intersect at every single point along their path. So there are infinite solutions. So why does any of this matter outside of a math class? I mean, really? Well, it's because these systems are incredibly powerful tools for modeling the real world.
This right here is where the math becomes this amazing tool for making sense of things. For a business, maybe one line represents your total costs and another line represents your revenue. And that point where they cross, that's the break-even point, the exact moment you start being profitable. For an engineer, these equations can model all the forces in a bridge to make sure it's safe and stable. It's used everywhere, from optimizing traffic flow to helping you compare job offers to balancing chemical equations in a lab. This stuff isn't just abstract theory. It is a very real, very practical toolkit for finding answers.
You see, at the end of the day, systems of equations are all about finding where different conditions meet a perfect balance. They give us a precise, powerful way to model relationships and find solutions. So the only real question left is, what problem will you model and solve first?